Yeah, I'd like to welcome you guys all thank you for joining us for today's presentation on the use of weights when analyzing survey data, descriptive statistics versus regression modeling with Dr. Brady West. Today's presentation is brought to you by the Social, Behavioral, and Economic COVID Coordinating Center, or SBE CCC at ICPSR. For those of you who are not familiar with us, we're a center for communication and collaboration amongst NIH-funded projects undertaking social, behavioral, and economic research on COVID-19. We promote an innovative cross-disciplinary approach to COVID-19 research across the behavioral and social science community, multiple NIH award recipients, and the public. And if you haven't already, we hope you'll take a moment to visit our website. You can join our mailing list and receive our semi-annual newsletter, and along with other occasional updates. With that, I'd like to introduce our speaker before turning things over. So Dr. Brady West is a research professor in the Survey Methodology program located within the Survey Research Center at the Institute for Social Research at the University of Michigan. He earned his PhD from the Michigan program in Survey and Data Science in 2011, and his current interests include the implications of measurement error and auxiliary variables and survey paradata for survey estimation, selection bias in surveys, responsive or adaptive survey design, interviewer effects, and multi-level regression models for clustered and longitudinal data. And with that, Brady, I will turn things over to you.
Okay, great. Thanks, John. Thanks again for the invitation to provide this webinar today. Up here on the initial slide, I have my email address. That's probably the easiest way to get in touch with me if you have any questions or maybe questions came up that we weren't able to get to today. Feel free to shoot me an email after the webinar is over, and I'd be happy to communicate with you further about some of the issues that we'll be discussing today. So as everybody's hopefully aware, we'll be talking about some sticky issues with using survey weights and analyzing survey data, specifically thinking about descriptive statistical analysis versus regression modeling, and what we need to think about regarding survey weights when we're thinking about performing these different kinds of analyses. So that's going to be our primary focus. As John mentioned, you're welcome to type questions in the chat, but I'm going to try to get through the material so that we touch on everything before leaving time to go through the chat questions and having a general question and answer session at the end. So I'll address questions after we get through all the material rather than in the middle, just to make sure that we get through all of it within the time that we have today. Okay, so any kind of discussion about statistical analysis using survey weights has to start with a general introduction of where weights even come from in the first place, so that we have an appreciation of what those weights are accounting for and why we worry about using them when analyzing data from complex sample surveys. So when we're performing weighted analyses of data from probability or even non-probability samples, as we'll talk about at the end of the discussion today, generally we're trying to make inference about the features of some finite population, where if we had the resources, we could go out and enumerate everybody in that finite population. We typically don't have those kinds of resources, so we draw a probability sample, or we just collect data or gather data from people in that population. And then based on those data, we try to make inference about these finite population parameters. Usually this is based on some form of confidence interval approach. And there's a quote here from Jerzy Neyman in a very important paper in the early 1930s, where he coined this term confidence intervals. And a key part of forming these intervals for finite population parameters is the calculation of these weighted point estimates, or these survey weighted estimates of whatever the quantity is that we're interested in. We'll just call that theta in general here. So theta could be a proportion, it could be a mean, it could be a total, or if we're talking about regression analysis, it could be an odds ratio, regression coefficient, you know, a scaling factor or a loading factor in structural equation modeling, whatever it might be. That's a parameter that we're interested in. We need a weighted estimate of that parameter that represents our best estimate of what that parameter would be if we had, in fact, collected data on everyone in the population. So really, the weights give us a mechanism for making statements about parameters in that finite population, and calculating these weighted estimates is critical to forming confidence intervals in this way. So it's also very important in design-based analyses to use correct critical t-values when forming these intervals, and to calculate correct variance estimates when forming these intervals that adjust for the features of the complex probability sampling. That's not the primary focus of today's webinar. Really, we're going to talk about choices to use weights when conducting descriptive and regression analysis. But these are key other pieces of design-based inference that I won't necessarily be touching on today. Our primary focus is going to be on whether and how to use weights in performing these kinds of analyses. So what do these weights typically account for when we're analyzing survey data? Weighting is usually used to compensate for three major pieces. First of all, unequal probabilities of selection. So the idea that different sampled cases from the population may have different probabilities of being included in a sample. So some cases may have been oversampled in an area of probability sample. Geographic areas may be sampled with probability proportionate to size. There's a variety of different sampling mechanisms that can give rise to these unequal probabilities of being selected for a sample. And we'll come back to these issues with non-probability sampling as well. But that's one of the major components of sampling that weighting is used to account for, is the fact that not everybody has the same chance of being selected for a given sample. Second of all, weights could also typically compensate for unit non-response, or the fact that a given sampled element from the population chooses not to respond to the survey request. So this is different from item non-response, where somebody might respond to a survey request, but then fail to answer particular questions within the survey. Weighting typically compensates for unit non-response, where an individual who's sampled or an element that's sampled doesn't participate in the survey data collection at all. So that's the second piece. The third piece is some form of calibration adjustment, where the weights that account for the first two components, unequal probability of selection and non-response, are adjusted further to make sure that the weighted sample is in alignment with known population quantities. So if you know distributions, for example, of age or sex or education in the target population that you're interested in, you further calibrate those weights incorporating the first two components here so that your weighted sample looks exactly like the target population in terms of those known distributions. So that's usually a third step of adjustment that's used to make sure that you're talking about the population that you're truly interested in. So the typical weight that you see in one of these survey data sets kind of rolls all three of these pieces into a single variable that you then employ for either descriptive or multivariable analyses. Long story short, weights are really used to minimize the bias of sample estimates and compensate for any bias that might be introduced by unequal probability of selection or differential non-response, or the fact that your weighted sample doesn't exactly match what's known about the population in terms of certain distributions. Weights can also compensate for non-coverage, the fact that you're using a sampling frame that doesn't necessarily cover the true population. So they play a very important role in cleaning up some of this bias that comes from these issues of sample selection that we see here. So as I mentioned, weights that you see in survey data sets typically incorporate all three of these components: unequal probability of selection, non-response, and post-stratification. So there's typically a component of the weight that accounts for the unequal probability of selection. I'll call that weight selection. There's a component of the weight that accounts for sample non-response. I'll call that weight NR. And then there's a component of the weight that accounts for that post-stratification or calibration adjustment. We'll call that WPS. The typical final weight that you see in these survey data sets is the product of all three of these pieces. So a weight accounting for unequal probability of selection, a weight accounting for differential rates of response across different subgroups, and then that additional calibration adjustment factor. All three of those components are multiplied by each other to form that final overall weight, which again typically occupies a single variable in these data sets that you'd have to determine from reading the documentation for the data sets. And I've included a couple of articles here at the bottom of slide 5 that are really nice overviews of some of the issues that arise with forming weights in this way. So Rick Valiant's article about the effects of multiple weighting steps on your standard errors and how you can account for uncertainty in each of these adjustment steps and your standard errors. Very nice piece. And then this other article by David Haziza talking about how weights are constructed in surveys just provides a big picture overview of this process, and a very readable article in the journal Statistical Science. So if you'd like to read additional details, certainly take a look at one of these articles. So that initial weight, that sample selection weight, maps your probability sample to the population that it's supposed to represent. So the way this works, suppose that a given sample element I was selected with some known probability f sub I. So in probability sampling, all the elements in the population, we can calculate a known non-zero probability of being selected into the sample. And those quantities are known with certainty. So suppose we have that probability of selection f sub I based on the sample design. Then sampled element I represents 1 divided by f sub I, or the inverse of that selection probability, elements in the target population. So you would count element I in the analysis by giving a weight that represents the inverse of that probability of selection. So a simple way of thinking about this, take the example where a sample element was selected with probability 1 out of 10. So they had a 1 in 10 chance of being selected into the sample. That individual sampled may be interpreted as representing 10 other elements in the target population. So that individual represents themselves and 9 other elements in the population. So simply inverting that selection probability would give an initial selection weight of 10 for that particular individual. So that's the way that initial selection weight works. The tricky part is calculating those known probabilities overall based on a given sample design. A lot of people spend a lot of time maintaining those probabilities of selection for a given complex sample design. And again, we'll come back to non-probability sampling a little bit later. So this is an example from one of Michigan's major national studies, the Health and Retirement Study, in the way that sample selection weight gets computed. So in this table, you see 4 different hypothetical sampled IDs, okay? And in addition, you see the race or ethnicity of a given respondent, and you see the number of age-eligible respondents within a household, okay? So for these 4 different IDs. Now, for these 4 different IDs, notice that there are kind of 3 selection pieces here based on the complex probability sampling design used for the HRS. The initial selection weight for household selection, okay, the probabilities of selection of the households, notice that those are all equal for each of these 4 different sample IDs. So each of these 4 individuals, their sampled households had the same probability of being selected, called an equal probability of selection mechanism. And so at the stage of household selection, everybody has the same weight because everybody had the same probability of being selected, 1 out of 2,000. So if we just invert that, we get 2,000 as a household weight. However, given the HRS sample design, there's oversampling of certain types of race ethnicity subgroups, and there could also be a different number of eligible individuals for selection within each of the sampled households. That's something that's out of the HRS control, given what households are actually selected. So in terms of oversampling, African-American individuals in this hypothetical example are sampled at a rate that's twice as high as other individuals. Okay, that's by design so that we have an oversample of African-American individuals. In that situation, those other individuals who are sampled at a lower rate within the households, they need a higher weight to account for that lower probability of selection within households. And that's where you see that additional part of the selection weight for oversampling of 2 for individuals who are not Black. Individuals who are Black, they would just get a weight of 1 in that case. And that accounts for that 2 times higher probability of selection within households. Then finally, because households may have different counts of eligible individuals and the HRS just wants 1 individual sampled from that household, you see that in individuals, in households where there are 2 individuals, 1 out of 2 individuals will get randomly selected. So again, if we invert that, we have a selection weight of 2 accounting for eligibility. If there's only 1 person in a household, that person gets selected and their weight is just 1. They had a probability of 1 of being selected within that household. Same thing for household C, where there were 2 eligible individuals, 1 out of 2 was selected. So there's an additional compensation weight of 2 for that part of the probability of selection. When you put all these pieces together, representing the overall probability of selection, you see that final selection weight in the last column there. That's the selection weight that represents the first individual represents themselves and 3,999 other people in the population. Second individual, themselves and 1,999 other individuals in the population, and so forth. These are the initial selection weights that go into that final overall weight that's used for estimation. Now, those are the weights for the probability of selection, but not everybody who's selected and then invited to participate in the survey is actually going to respond. So response rates in these major national studies are going down. They're trending down over time. It's becoming harder and harder to try to get these individuals to participate. So there's an additional adjustment of those base selection weights to account for an additional probability of responding to the actual survey request, because not every individual is going to respond to a survey request. In this framework, that probability of responding to the survey request is treated like another probability of selection, the same way that sample selection was handled. So this random act of responding to the survey request is thought of as another random selection step. And so we try to estimate the probability of responding to the survey conditional on having been sampled. And then we can invert that estimated probability as an additional adjustment for probability of self-selecting to respond to the actual survey. So in that situation, we're trying to fix biases that are introduced by differential non-response across different subgroups. And there's a simple deterministic expression here of the bias in a respondent mean, or the difference between the respondent mean and the overall population mean. You can express that as a product of the non-response rate, 1 minus the response rate for the survey, multiplied by the mean for respondents minus the mean for non-respondents. So the key takeaway point about this bias expression here is that the amount of bias in a respondent mean is not just a function of the response rate, but also of the differences in means between respondents and non-respondents. So that's a key part of non-response bias adjustment. We'd like to make adjustments based on variables that are related to not only the probability of selection, but also the key variable of interest, okay, to fix up that second piece, that difference between respondents and non-respondents. So generally, there are two common methods of developing adjustments for non-response. One is weighting class adjustments, and one is response propensity weighting adjustments. Both of these approaches are targeted at predicting the probability of responding conditional on having been sampled. Again, like an additional stage of selection into the overall now respondent sample. So in weighting class adjustments, you use the values on known auxiliary variables that are available for the entire sample to form cells of sampled individuals. And you cross-classify respondents and non-respondents based on those known categorical variables. So everybody in the sample is placed into one of these cells defined by these cross-classifications of these known auxiliary variables. Then you assume that the probability of response within the cell is the response rate for those sampled cases who are grouped into cell C. And there's an article in Survey Methodology, some other work that's been done since that article to argue that in theory, these response rates within each of the cells should be weighted. That is, they should incorporate the weights from the first stage of selection here, that sample selection stage. Those should be used to estimate these probabilities of response within each of these weighting cells. So you then compute that second piece of the weight, the non-response adjustment, as the reciprocal of the response rate within each of these weighting classes, the weighted response rate. So that WNR piece of the final overall weight is just the inverse of that predicted response rate within each of the weighting classes. And again, there have been arguments that that should be a weighted response rate. Okay, so simple idea, and same idea as the probability of selection. Again, non-response is treated like another random selection process, only now the sampled units are self-selecting to participate in the survey, and we're trying to estimate these rates of response. And so there's uncertainty in these estimates that we can account for in the variance estimation, but it's just another adjustment for probability of selection now at the stage of being sampled. Response propensity adjustment for non-response works in a very similar fashion. We just don't form those weighting classes necessarily to begin with. Rather, we fit models that predict an indicator of responding to the survey request that's available for everybody in the sample. So people who respond get a 1 on this indicator. People in the sample who do not respond get a 0. And then we use auxiliary variables to fit a regression model that allows us to predict the probability of responding to the survey. And ideally, we would like to use predictors in these response propensity models that both predict non-response and are associated with the variables that we're interested in. That's where we're going to get the most bias reduction from this weighting adjustment step for non-response. Okay, so this is a more flexible method because we can use any kinds of predictors. They don't have to be categorical. We don't have to use a parametric model. We could use machine learning techniques, whatever allows us to predict the probability of responding as a function of these known auxiliary variables. We can calculate response propensities in that way. And following this approach, the non-response adjustment is simply calculated as the inverse of that predicted response propensity given this fitted logistic or probit or classification tree model or whatever the case may be. We invert that predicted probability to get this second non-response adjustment piece. Sometimes there are weighting classes created based on deciles or quintiles of these predicted response propensities, and that smooths out some of the extreme adjustments that can come about if you're just using the raw predicted probabilities. Sometimes these predicted response probabilities are grouped into these classes, and then you look at the median for a class or something like that. That smooths out some of the extreme values that can arise from this particular process for non-response adjustment. Okay, so we have those first two pieces of the weight, the selection weight, the non-response adjustment factor. Then we have this final step where we're trying to align our weighted values or our weighted sample with known features of the population. This is usually a simple form of adjustment where if we're given a known count for a particular group in the population, say males or something like that, we look at the ratio of that known count to the estimated size of that population based on the weights that we've computed so far. So if you look at this expression for this final third post-stratification adjustment, and this is one way that we can perform calibration, there are many others, but if you look at this expression, that denominator is the sum of the products of those first two pieces. So if we had stopped after those first two weighting adjustment steps, and we looked at estimates of the counts of the population in certain cells defined here by little l, do those estimated counts match pretty well with known counts for the target population based on the census or based on some other large survey like the American Community Survey? We look at this ratio of the known quantity in the numerator obtained from some external record to the estimated count within that particular post-stratification cell in the denominator based on the weights that we've computed so far. If the weights that we've computed so far are doing a good job of mapping us back to the population after sample selection and non-response, these ratios are going to be close to 1. And there's not going to be a lot of need for additional adjustment. If, however, there's still a lot of additional adjustment necessary, these ratios are going to vary around 1, meaning that some cases need to get upweighted, some cases need to get downweighted a little bit, again, depending on what's known for the target population. So this is one simple form of calibration known as post-stratification, but this is where we get that final adjustment piece for the overall weight to make sure that our weighted sample is in alignment with the target population that we're interested in. Okay, so different survey programs will use different forms of calibration adjustment. Some of you might have heard of raking or generalized regression estimation. There's a number of different ways to do this. But this is nice because it not only aligns our sample with the target population, but it results in gains in precision of our estimates because we're aligning to known information. And there are ways to achieve those gains in precision by inputting the post-stratification information to variance estimation software. Again, that's not our focus today, but this kind of calibration is very effective in many ways. So this is just showing you a picture there of these 3 weighting steps combined, going back to that HRS example. For each of those 4 cases, using a weighting class adjustment, you see what non-response adjustment cell they fell into, and then you can see what post-stratum they fell into for the purpose of post-stratification adjustment. So given the non-response adjustment cells that you see here, case A, for example, the inverse of their probability of responding was 1.3. That's where that non-response adjustment comes from. Second person, The inverse of their probability of responding in their cell, 1.15, and so forth and so on. Then attempting to calibrate these individuals with what's known about the population in terms of age, being a male, and marital status. We have those additional post-stratification adjustments in the third column here. And you can see that those numbers hover around 1. So they're very close to 1. Minor adjustments were needed to make sure that this weighted sample was in alignment with the overall population. So in the end, for the HRS weights that you see in the data set, you see the products of these three pieces. 4,000 times the non-response adjustment times the calibration adjustment, that gives us 5,408, and so forth and so on for the other cases in the data set. This guy here is what you typically see as a secondary analyst in these large national survey data sets. You're not typically going to see each of these three pieces. Usually that's only maintained internally. And for the purpose of data users and producing data for the public, we're only going to typically see that final weight. And that's the final weight that we would use as input to our descriptive estimation for our regression modeling and so forth. And it's just important to keep in mind the purpose of that weight. Again, it's mapping our sample back to what the population would look like if we had been able to collect data on everyone in the population. So whatever person A says in the survey speaks for themselves and 5,407 other people in the target population. That's the whole principle of the weight in the first place, is to allow us to make statements about what the population looks like, given what we already know about these individuals and their probabilities of selection, their probabilities of responding, and how well aligned they are with other known features of the population. Okay, so that final weight, again, is typically in a single variable in the public use survey data sets that we would be working with in practice. And that single final weight is what we would input for our estimation procedures that we're going to be talking about. Now, when you use weights in estimation, okay, there are trade-offs. Okay, the more variable that those weights are, so we saw a lot of variability just in these 4 weights, right? Those weights range from 2208 all the way up to 10,600. So there's a lot of variability here. The more variable those final weights are, the larger our variance estimates are going to be. Okay, so this is known as an unequal weighting effect, or a loss in precision due to weighting. Leslie Kish formulated what's really an upper bound for this loss of precision due to the variability of the weights that can be expressed here. Long story short, this quantity, this squared coefficient of variation of the weights, is known as this factor L. And 1 plus L is the multiplicative variance inflation of a descriptive estimate due to the use of variable weights in estimation. Okay, so as an upper bound for that variance inflation, we would multiply our expected variance by 1 plus this quantity here, L, to get a sense of how much variability in the weights is inflating the variances of our weighted estimates. Okay, so it's not a free lunch. We're using those weights to reduce bias, but the more variable those weights are, the higher our variance estimates are going to be. So data producers do the best that they can to release weights that have minimal variability, but still do the best reduction of bias that's possible when they release weights to the public. Okay, so this is an important consideration that we'll come back to, trying to deal with this variance inflation when you're doing analysis. But it is, when you're using weighted estimation, this is a trade-off. You do experience inflation of the variance in your estimates. And this quantity here, which could also be expressed as, if I write the coefficient of variation squared, that can also be expressed as the standard deviation of the weights divided by the mean of the weights, quantity squared. So that's something you can compute on your own. When you open up one of these data sets, just calculate the standard deviation of the weights, divide by the mean, and square that quantity. That will give you this L factor. And then you can add 1 to that L factor to get a sense of the variance inflation due to the use of weights in estimation. It is going to be a little bit smaller for subgroups when you're focused on subgroup estimation, but you still will get some kind of variance inflation associated with the use of weight. So again, there's a trade-off here that you experience when using the weights in estimation. This is just a little example of oversampling. So in this particular case, you can see 4 different sampling strata. And suppose we're interested in the Hispanic population, and there's differentials among the 4 strata in terms of the percentage of the population, the percentage of the Hispanic population that comes from each of those 4 strata. So by design, you might make the decision to oversample from the strata that has more of the Hispanic population present. Again, by design, as part of a probability sample, you might make that decision. And as a result of that decision to oversample, you have to develop weights to account for that probability of selection. So you can see the differential weights here that would be computed to reflect those oversampling rates within each of these 4 strata. And you can see that most of the Hispanic sample, as a result of this sampling scheme, is coming from that 4th stratum. But again, there's a trade-off in doing this. You're getting more sample from that stratum, but you're introducing more variability in your weights. And if there's more variability in your weights, the variance of your estimates will increase. So this is just walking through that L calculation for a hypothetical sample of size 1,000 under these oversampling rates. And you can see that that L factor ends up being 0.284. So if I add 1 to that, I get 1.284. I would expect the variances of my descriptive estimates as an upper bound of that variance inflation to be inflated by about 28% or multiplied by 1.284 as a result of the use of weights in estimation. Okay, and again, that's an upper bound. If the weights have a correlation with your variables of interest, you're going to get more bias reduction, and that variance inflation won't be as severe. This upper bound, this 1 plus L calculation, assumes that the weights are independent of your variables of interest. So it really is a maximum possible variance inflation. And the more informative your weights are about your variables of interest, the less this variance inflation is going to be. It really gives you a diagnostic, like a maximum on the amount of variance inflation that you might experience from using the weights in estimation. Okay, so just again, to reinforce that point that when you use the weights in estimation, you do have to have this trade-off in terms of the precision of your estimates. So now that we have these final weights, what do we do with them in analysis, right? We have this decision, should we perform a weighted analysis or should we not? And with weighted descriptive estimates, the calculations are pretty straightforward. So if you want to estimate a mean or a proportion, you simply multiply each individual's contribution to that estimate by their final survey weight that was computed as a result of that process. So in this expression for a weighted mean here, you see that in the numerator, we're just summing all the data values on some variable of interest y, but each individual's contribution is multiplied by that population scale weight. So we're not saying what is the sum of the data values for the sample. We're saying, what are we estimating the sum of those data values to be for the target population? And then we simply sum the weights to get an estimated size of the target population in the denominator. That gives us a weighted point estimate of the population mean y. Okay, same thing for estimating the element variance. We multiply each individual's contribution by their final survey weight. We use the weighted mean instead of the unweighted sample mean, and that gives us a population estimate of the element variance on a variable of interest, call it y. Simple linear regression coefficient. Some of you might recognize that expression, the sum of the cross products of the dependent variable in the predictor in the numerator, and then the sum of the squared values of the predictor in the denominator. Each individual's contribution just multiplied by their final survey weight. Again, we're trying to estimate what the population would look like using those final survey weights and mapping our sample back to the population. So these weights will give us an unbiased estimate of what the population looks like with respect to the sample design that was used. Okay. So this table just gives you a sense of the distributions of these weights and what they might look like in different data sets. So here, these are distributions from the National Comorbidity Survey, the National Health and Nutrition Examination Survey, and then the Health and Retirement Study. You see that the NHANES and the Health and Retirement Study, they release data sets with weights that are on the population scale, allowing for this population level inferences, estimation of population totals. In the National Comorbidity Survey, notice that the mean of the weights was 1. That's an example of what's called a normalized weight. Okay, so that's a weight where the sum of the weights is equal to the sample size. The weights have been scaled to sum to the sample size. That's a bit of a historical practice that was from a time when the survey software is nowhere as powerful and capable as it is today. And weights weren't typically handled correctly by the software procedures. It was kind of protecting analysts against themselves. So it's not really necessary to do that nowadays, to release data sets where those weights have been normalized like this, because it prevents people from estimating population totals. The weights are no longer on a population scale. Most other estimates will be fine, but totals, it makes it hard to estimate totals. So we have to be careful about that. And if you are interested in estimating population totals, those normalized weights have to be scaled back to the population level. And you might have to work with the data producer in order to do that. But means, proportions, other quantities that are very common, those are unaffected by normalizing weights. Only totals are really affected. And that's what this slide is saying here. Typically on population scale weights, if you sum those weights, you get an estimate of the population size. But some data producers will scale them by dividing those final population weights by the average weight in the data set. That's what gives you weights that sum to the sample size. And again, that's fine for the vast majority of estimates, but it prevents you from calculating estimates of population totals. Okay, so that's something just to be aware of when you're looking at descriptive calculations for your weights. Just see if the mean of the weights is 1. And the only red flag that should really be set off there is that, okay, if the mean of my weights is 1, I'm going to have a hard time estimating population totals. Okay, everything else, you'll be fine with normalized weights. Okay, so what do we do when it comes to regression? With descriptive estimation, so if you're looking at means or proportions or totals, there's generally very little debate in the literature about the need to use weights when you're estimating descriptive parameters, especially if those weights are correlated with the variables that you're interested in computing descriptive estimates for. Okay, so there, weights are really truly designed to give you unbiased estimates of those descriptive quantities, and it's usually a good idea to use them if those weights are correlated with your variables of interest. And we often refer to that as the weights being informative for your variables of interest. So if the weights are correlated with the variables that you're computing descriptive estimates for, the weighted estimates are going to differ from the unweighted estimates because they're reducing bias. If there is no correlation between the weights and your variables of interest, the weighted estimates will look very similar to the unweighted estimates. And going back to our earlier discussion, if that's the case, you might be harming yourself, because remember, those weights, the use of those weights in estimation is introducing increased variance for the estimates that you're computing. It's inflating the variance of your estimates. So if those weights are not correlated with variables of interest, but you're still blindly using them in descriptive analysis, you could just be inflating the variance of your estimates without achieving any reductions in bias, and ultimately producing lower quality estimates as a result. So a good descriptive step whenever you're doing these kinds of analyses, check the correlations of your weights with the variables that you're interested in, and compare your weighted descriptive estimates with your unweighted descriptive estimates. And then look at those differences compared to the changes in the standard errors of your descriptive estimates, and see if you're getting a notable shift in your estimate relative to the change in the standard error from using the weights in estimation. That's usually good practice to make sure that you're not harming yourself by just adding noise to your estimates via the use of weights in estimation. Generally, there's a lot more debate regarding the use of weights when fitting regression models to survey data. So not as much debate with descriptive estimates outside of what I had just suggested, looking at the weighted and the unweighted estimates. But with regression models, there's been a much longer history of debate about whether weights should be used or not in these kinds of analyses. So again, when our focus is on estimating what a regression model would look like in a finite population of interest, we're in this design-based finite population framework where we are interested in trying to come up with estimates of what the population would look like and what regression models would look like in that target population. Model specification is generally very important. So when you do a poor job of specifying your model, but then you use weights in estimation, which ensures that you're computing unbiased estimates with respect to the sample design of what that regression model would look like, you end up with unbiased estimates, which is good, of a regression model in a very bad model. Okay, so if you've misspecified that model, what you're going to get is an estimate of what that regression model would look like in your population, but it's not going to fix the specification errors that you're making. So you're getting a nice unbiased picture of what a really bad model would look like in your finite population. So very important to be careful with model specification, because if you do a good job of specifying your model and you combine that with weighted estimation, you might get unnecessarily inflated standard errors, right? Same problem that we talked about earlier, more variability in the weights, more variability in terms of your weighted estimates of regression coefficients. And if you do a good job of specifying your model, you may not need to use those weights in estimation. They may no longer be informative about the model that you're fitting. Okay, so in that particular case, you might be able to get by with an unweighted model, still accounting for other complex sampling features like stratification and cluster sampling, but the unweighted model may give you a very good estimate of what that regression model looks like in your target population, and you don't need to use those weights in estimation. Remember, those weights are giving you protection against bias introduced by sample selection, non-response, okay? But if you do a good job of specifying the regression model, they may not be necessary, and they may not change your estimates at all, okay? So Korn and Grabart have a nice example of this kind of debate, if you will, in their 1999 book on analysis of health survey data. I think given time constraints, I'm just going to jump to the example that we're talking about. But if you look up that example, you'll get a good picture of these different scenarios where, you know, you do a good job of specifying a model, you use the weights and estimation, and all you see is that your variances are inflated. But weighted and unweighted estimates of a model look very similar, okay? Versus misspecifying a model using weights and seeing how much those weighted estimates change compared to the unweighted estimates, okay? So the general recommendation when you're fitting regression models in practice is to think about what the models look like when they're fitted with and without weights, not just to camp out in one of these areas and say, I'm only ever going to use weights, or I'm only never going to use weights, but appreciate the fact that we can fit these models very quickly in the software and do some diagnostics to see what the estimates look like with and without accounting for these weights. Large changes in parameter estimates would suggest potential model misspecification, and that at the very least, you should be using weights to make sure that you're getting unbiased estimates with respect to the sample design that was actually employed. So again, you're in that picture where I don't know what the right model is, but I want to make sure I'm getting estimates of what that model would look like in my finite population. That's the protection that the weights are giving you, okay? Small changes in parameter estimates, as opposed to large changes in standard errors, would suggest that you've done a really good job of the model specification and that you'd have minimal problems with using unweighted models. So again, you could get by with better estimates without using those weights to actually calculate your regression coefficients. Some go so far as to say, use the weight as an actual covariate in the regression models, which helps to make the sampling mechanism ignorable in some sense, or use variables that were used to compute the weight as predictors in the regression model. That's one possible approach, but it's dangerous. Again, it puts more pressure on making sure that that model is correctly specified to really make those weights uninformative with respect to the model being fitted. And Ken Bullen et al. Did a nice review piece on different ways of checking for whether or not weights are necessary when you're fitting a regression model. So there have been several tests proposed over the years for seeing whether or not weights are necessary, and they reviewed the properties of some of these tests. That's a nice article to read. I'm going to go over a simple approach, one of these tests to check for the need for weights when fitting regression models, but there are others that are out there. This one is just fairly straightforward to implement in practice. So this useful kind of check on whether or not you need weights when fitting a regression model survey data. What you do is you perform an unweighted analysis. Okay, so you turn the weight variable off if you're using some kind of survey software. You still want to account for other design features like stratification, cluster sampling, replicate weights, whatever information the data producer has given you, but you turn off the weights. So you're not calculating weighted point estimates. In the regression model that you're trying to fit, okay, you include all the predictors that you want, could include interactions, nonlinear terms, whatever the case may be. You have all the predictors that you're interested in. To that model, you add the weight variable itself, and then you add two-way interactions of that weight variable with each of the other predictors that are already included in that model, okay? So here's a step-by-step example of how one might do this. I'm using Stata here, but you could use whatever software you wanted to do this kind of check. I'm using data from the National Health and Nutrition Examination Survey. So in step one, I specify my design features to the software, but I don't turn on the weight. So I leave the weight variable out of that specification. Then I write the code for my model of interest, including my dependent variable and whatever my predictors are. So in this case, I'm modeling BMI as a function of age, education, marital status, and your blood pressure category. Okay, that's my substantive model of interest. To check for the need for weights, to that model, I add the weight variable itself, this medical examination weight that you see here, and then all the two-way interactions of that weight variable with all of the other predictors in my model. Using stata syntax here, the C dot just means that that's a continuous variable in the interaction term. The I dot means those are categorical variables. That's just stata notation. Don't worry about that. The key point is that we're adding the weight and its two-way interactions with every other predictor that's specified in the model. And the basic conceptual idea here is that by adding that weight and its interactions, we're seeing if the weight moderates the relationships of our predictors with the variable of interest. So as the value of the weight changes, does the coefficient for a given predictor change? We're testing for that moderation to see if the value of the weight changes the value of our coefficient, checking to see whether or not the weights are informative. So we add all these terms that I added here in red. You fit that model, again, without having the weights on and with all these additional terms, you fit that model, and then you perform an overall test of all those additional parameters that you added to the model involving the weight. So that's what I'm doing here with this test statement. After I fit the model in stata, I'm doing this multi-parameter walled test where I test all these additional terms and I test whether or not those weights are moderating the values of my coefficients in this particular model. So the null hypothesis that I'm testing here is that all the coefficients for these additional terms are 0. In other words, the weights aren't telling me anything about the coefficients in my model of interest, versus the alternative where at least one of those coefficients is being moderated by the value of the weight, which would suggest that I would need to use the weights in estimation because they carry information about some of these coefficients. So I perform that overall test. And in step 4, I just look at the results of that test. Again, it's design adjusted. I still have my other design features on within the software. In this particular case, I would fail to reject the null hypothesis, given that p-value, that all of those additional terms are 0. So that's telling me that in this example, all those coefficients are not being affected by the weights in any way. As the values of the weights are changing, the values of those coefficients are not changing. So this reassures me that I'm not really getting any additional information from using the weights in estimation in this particular regression model. So very handy test, very easy to implement in whatever software you're using. This slide just shows you estimates from that example that I was just looking at, the unweighted estimates and the weighted estimates, in addition to the unweighted standard errors and then the weighted standard errors, following these two different approaches. What you see here is that the weighted estimates are hardly changing, but the standard errors are consistently increasing. So I'm in that second scenario that I was talking about when comparing unweighted and weighted regression models where the coefficients look very, very similar, but the standard errors are consistently getting larger from the use of weights and estimation. And that's going back to what I was talking about earlier with that variance inflation due to the use of weights and estimation. So in this case, I'd ultimately be producing better estimates that are still giving me the same general conclusions about these relationships of interest by going with the unweighted model. That still accounts for the other sample design features, just not using the weights for calculating the point estimates. Okay, so this is an example where I don't see strong evidence of a need to use the weights in estimation. You'll certainly encounter other examples where the result of that test is significant, and it certainly seems like the weights are informative about the model that you're fitting, and thus you should use those weights to calculate those design unbiased point estimates. Okay. An alternative weighting approach, and we're about to wrap up here, so there'll be some time for questions. An alternative weighting approach was proposed by Danny Pfefferman about 10 years ago, this kind of Q weighting idea. What you would do here is regress that final survey weight variable in your data set on all the predictor variables of interest in your regression model. So you're literally treating the weight variable itself like a dependent variable in a regression analysis. And then you save predicted values of that final weight variable as a function of the predictor variables in your data set. So you have a column of predicted values of what the weight is expected to be as a function of those different predictor variables. You take those final survey weights given to you by the data producer, and you divide by those predicted values that you've saved in the data set, or the expected values of the weights given the predictors. You then use those adjusted weights in your design-based analysis. So you're taking the original weight, dividing it by its expectation, and you use that as the weight variable in your design adjusted analysis. And we've included an illustration of this in our book called Applied Survey Data Analysis. What Pfefferman showed was a simulation study and some real examples suggesting that this approach yields weighted estimates that, again, give you bias correction like we talked about earlier, but with improved efficiency, that is, lower standard errors. So if you go back to this example here, that kind of approach is going to reduce the variance inflation that we're seeing. The weights are being scaled by their expectations to reduce the amount of variance inflation that we're seeing, but still preserve bias reduction that the weights were originally designed for. Again, something very straightforward to implement in practice, very handy, very nice statistical properties designed to reduce those variance inflation effects of the use of weights when fitting these regression models. So that's another nice practical approach that you can use to deal with this variance inflation issue. Okay, the last thing that I want to touch on before we have some time for questions is, what do we do about non-probability samples? Okay, so thus far, I've largely been talking about probability samples where we have these known non-zero probabilities of selection. We can use those weights in estimation. We can calculate unbiased estimates with respect to the sample design. In non-probability samples, we don't really know what those probabilities are. You know, we have volunteer samples, convenience samples, snowball samples, quota samples. All of these, we don't really have control over the selection probabilities. So the basic idea that's currently being proposed in the literature and that individuals are studying right now is this kind of quasi-randomization approach. Okay, and the idea, the way that this works, you append a large probability sample that includes identical covariates and final survey weights, like we saw in HRS, associated with that probability sample. You append that data set to your non-probability sample. And in the non-probability sample, all those cases get a weight value of 1, as opposed to the actual weight values in the larger probability sample. Then you create a binary indicator of belonging to the non-probability sample in that stacked data set. So you have a 1, 0 variable, 1 for everybody in the non-probability sample, 0 for everybody in the probability sample. You then fit a weighted logistic regression model to that binary indicator using those common covariates that are measured the same way in both data sets. And you save the predicted probabilities of belonging to the non-probability sample in the data set. There are some additional technical bias adjustment steps that are also needed there. I'm not going into detail about that here, but there's software that will do that part for you. So given those predicted probabilities, you then invert the predicted probabilities for your non-probability sample. Those become your pseudo design weights. It's like your probability of being included in that non-probability sample if you're part of this overall population represented by this stacked data set. You can then calibrate those pseudo design weights to known population totals, like we talked about with post-stratification, whatever adjustments you want, then you can compute your weighted point estimates of interest. You can also repeat this approach several times on replicate samples, like bootstrap samples of the original sample, for the purposes of estimating variances of those weighted estimates. There's a very nice description of this approach in Rick Valiant and Jill Deaver's 2018 book on survey weights and step-by-step guide to calculation for those survey weights that was published by Stata Press. Again, a very practical approach that makes it easy to develop these kinds of weighting adjustments for non-probability samples where, again, we don't have full control over those probabilities of selection. So this is a relatively straightforward way to do this. You just need to find that good partner probability sample with a lot of the same common covariates that you can use to develop those adjustments. But this is typically the general approach that would be recommended. And there are various enhancements of this approach that we've seen in the literature, doubly robust approaches that build on this. But this is the initial building block of this kind of approach. Okay. So I'm almost to 4. Sorry, I thought we'd have a little bit more time for questions, but I'm happy to go a little bit over 4. if people still have questions, and maybe we can start with questions that people had in the chat. So
yeah, so it looks like we thank you so much for that, Brady. And it looks like we have one from Claire on slide 19. She's asking, is there a common or a useful citation for the descriptive process?
for the descriptive process, you could use applied survey data analysis. You could use that Bolin et al. Article that I mentioned earlier. And I can send these citations offline. But there's also there's a it's an older paper at this point, but it's a nice paper. There's a 1983 paper that talks about like differences between design-based and model-based approaches and why design-based approaches are so important for descriptive estimates, by Mado et al. I can send that paper as well, just offline here. But yeah, there are definitely citations you can use for that. Yeah.
Yeah, if you wouldn't mind sending that to us, Brady, we can make sure that goes out with the slides in the recording.
Make a note about it here. Those are just a couple off the top of my head, and there's plenty of others, but yeah.
Looks like we have another question from Caroline. Can you go back and say a little bit more about what happens if the mean of your survey weights is 1 and what are the implications?
Yes. Okay, so I showed the one example here where the mean of the weights was 1. So that's again where the weights have been normalized, as it's often called. They've been scaled by dividing those final survey weights by the average weight in the data set. For means, proportions, correlation coefficients, regression coefficients, the vast majority of the stuff that we're usually interested in from a descriptive perspective, normalizing the weights is not going to have any impact on your estimates or your standard errors or anything else. Okay, you're going to get the exact same estimates, the exact same standard errors as if you were using the population scale weights. So everything's all good in that regard. The one drawback is that with normalized weights, you can't compute estimates of population totals. So if part of your descriptive objective is to estimate population totals and you see that the mean of your weights is 1, that prevents you from estimating those totals. And that kind of descriptive estimation is still a key cog of many descriptive survey programs, is trying to estimate, how many people in the population meet some criterion, or how many people have some characteristic, whatever the case may be. And normalized weights prevent you from doing that. So in all honesty, there's no reason to release normalized weights for any purpose these days, because we have all the necessary software. The initial kind of, again, user protection that normalized weights were designed for is no longer necessary, given the survey software that we have nowadays. So if you see a normalized weight in a data set, it's just to set off that flag in your mind about estimation of totals. Everything else should be okay.
All right, it looks like we have another question from Xiao Yu. And this is, so as for longitudinal surveys like HRS, are weight variables wave specific? And could you recommend some best practices when doing longitudinal data analysis with weights?
That's the $1 million question. So I see Yajwan's on right now. We're working on that problem right now. There's many things that have been recommended in the literature about what to do in that context. I think one thing that we're learning from the research that we're doing right now about dealing with longitudinal weights is that this so-called recommended best practice of just keeping the cases that have complete data over time as part of the whole longitudinal data set, and then basing your estimation, your trajectory estimation, whatever, on those so-called complete cases only, and like adjusting their base sampling weights in some way to account for all the other cases that were dropped. That's really not an ideal approach. I think what we're seeing in practice is that the best thing to do is use all of the available data from that longitudinal study. So if some people only contributed like half the waves, use their information. Use all the available data from the longitudinal study, and potentially those time varying weights may also carry information. That gets back to our question, are the weights necessary for a given regression model? So potentially use the time varying weights in estimation if it seems like they're adding information, but definitely use all available cases and put most of your effort into model specification and making sure that you're using all the available information. Those time varying weights may carry information, they may be useful, or they may not. That's where, again, checking for the need for those time varying weights is valuable, but you can use that in a multi-level modeling framework. You can use that in a marginal modeling framework. But the basic idea is to use all of the available information, including the time varying weights, to actually perform that kind of longitudinal data analysis. I think that's what we're learning from simulations and other empirical studies. So.
Great. Well, this is definitely giving me some ideas for potential follow-up webinars and topics that we can maybe dive into a little bit more. We have a bit more time. But with that, I know we're a few minutes over, so I thank you guys for sticking around, and I hope this was helpful. Brady, thank you so much for taking the time to go give us this nice overview.
I can still answer questions if there are any. I mean, I'm happy. It's up to you guys, so I'm fine with whatever. So.
Yeah, I think we could take maybe one or two more if there are any burning questions. Otherwise, you can always feel free to reach out to the SBE
please email
CCC
me.
help or Brady directly.
Yep. Yeah. Any other questions? Anything else in the chat, John?
No, I'm not seeing, just a lot of thank yous, and yeah, it seems to be very helpful. So.
Okay. Yeah, please feel free to email me if you have questions that are specific to a particular study or anything like that. More than happy to correspond with you about that. And we do provide technical support through the CCC. So, that there's a mechanism for providing that kind of support. So, yep.
All right. Well, thank you guys. And I hope you all have a good rest of the day.
Yeah. Thanks, everybody. This has been very nice. Thanks.